Hello, ma'am. I'm Zan Noor, and welcome to my presentation. The title of the project, this project is the design and simulation of a navigation system for a mobile robot application. Over the next few minutes, I will walk you through the concept of designing, implementation, and result of my indoor navigation system. So, the chosen application for this project is inspection and maintenance of industrial facilities. This application is both relevant and feasible, especially for the structured environment like warehouse, where autonomous robots can help with inspections and logistics. I have chosen a 2D drone simulation to simplify hardware constraint while focusing on navigation and software intelligence. So the robot operates a 20 by 20 boundary occupancy grid map that represent a warehouse, racks, and shelves. This help to simulate to the real world scenarios where the autonomous inspection is needed. So in this next slide, I have designed the robot as a point mass drone, meaning it doesn't simulate complex aerodynamic but focuses on navigation logics. The path is planned using a RRT algorithm, which allow the drone to move efficiently between the waypoint. The simulation update is estimated position in real time. All the operation like motion planning, SLAM updates, collision checking are handled within the MATLAB using the robotic system toolbox. This setup enables the realistic behavior in a control simulation. All the safety and ethics were considered. Despite this being a virtual simulation, the robot avoids all occupied grid cells, simulating the safe behavior around the people and infrastructure. In its motion is deterministic and slow, with a clear visual outputs. This ensures that predictable behaviors take being taken. And in a real-world application, this system can easily be in any incorporate safety protocols and error and dynamically it can obstacle avoidance for added the robustness. So the navigation system is being used is the MATLAB robotic system toolbox. So the key points of I have used is the boundary occupancy map for the map definitions. State space SE2 is to represent the robot's position and orientation, and the planner RRT for the motion planning. So the system validates a start point and a goal point, that detect the obstacles and update the map as the robot moves. SLAM integration allow the robot to build in its own map using the simulated perception and closely mimicking the real world robotic logic. So the RRT algorithm was selected for its efficiency in a cluttered environment. It built a tree of possible paths uses a goal bias to quickly find a valid route. Once the path is being planned, the robot move along the waypoint with a minimal deviation, and I have tuned the RRT parameter to a balance between the optimality and the planning speed. This ensures that the robot is fast but reliable navigation that is ideal for the inspection task. So the robot uses a simulated lidar-like sensors that perform a polar scanning. It emits the rays in a 120-degree arc with a 5-degree resolution and a 3-meter range. So the data from these rays are is used to detect the obstacle and update the SLAM map and the sensor figures. This perception system is critical for adaptive behavior and allow the robot to understand and respond to its environment dynamically. Now I will dive you into my code reviews. In this part of the demo, I walked you through the MATLAB code I have developed for my mobile robot project. The simulation model are drone navigating a 20 by 20 warehouse using the RRT for the path planning, boundary occupancy for the obstacle representation, and a basic SLAM process for the mapping the environment with the simulated lidar. So the code start with by 20 by 20 boundary occupancy map where each cell represent the 1 meter. The obstacles are added by the set occupancy function, which is in the toolbox. And the first I have defined the boundary walls, and then the internal obstacles are added up using the added rectangular obstacle function, which is the obstacles within the map. These simulated obstacles in represent the warehouse racks and columns. So The user is asked to select the start and point and the goal position on the map using the input. These points are validated to ensure that they are placed in a free space and they are mapped on the map with the red and the green markers. So user can click on any free space for the starting point, and if you want to go on any side, he can just click on that on that and on that side, and the simulation will animation will go through the with the avoiding the obstacles. So I defined the state as PESE2 for the RRT path planning setup. I also defined the state validator using the map and set the parameters such as validations distance. The planner RRT is configured with the custom parameters like max connection distance and the bias. The plan function. The plan function is set up for the from selecting the start to goal, starting the start to goal to avoid the obstacle based on the occupancy map. So and a new boundary occupancy map is being initialized for the slamming purpose. So the drone start with the known initial pose and I simulated sensor reading using the ray casting in a 120-degree field for of a view with a range of 3 meters, and a ray are cast every 5 degree. So the data is used to update is these data is used to update the slam map with the obstacle and the free space. This is the loop that is used for the slamming. In this so the In the loop, I update the slam map by marking obstacle from sensor hit and marking free space along the sensor race. A small amount of noise is added to estimated post to simulate the localization uncertainty, and this pose history and the pose history is being this is a pose history, and the pose history is being plotted on the slab figure. So after I have used the multiple figures for updating the slab, so these figures, like in this from here, these are the figures. Yeah, these are the figures in total I have used basically for the navigation for the debugging purpose. So after different perspective, the main view shows that the full path and drone position. The sensor view show the real-time lidar style rays, and the slamming view visualize, detect the obstacles and estimated drone path. Each figure is updated in a loop that move the drone through the plan. So another subplot I have make is the path course analysis in here. This is the path course analysis, and which is calculated by assuming the Euclidean distance between the consecutive waypoint along the path. This help to visualize the efficiency of the report. So this is my whole code. This is my rectangular base function that I've added on the top here. So I will run the code now and show you my result. So basically, as you can see, this is my main figure, drone navigation with RRT, and this is my console. So if I put this is my starting point, and if I put it here, the goal. So as you can see, I got multiple figures. You can see this is my simulation. This is my sensor reading I get, and this will getting update on every new path if it gone, and this is my total final path course. So I'm gonna run it again for making it complex. Uh, Here you can see if I put it here and the other one is here. So as you can see that the sensor readings are changing. The SLAM process is changing and the path is modified. As you can see, my all that is not being colliding is just avoiding the obstacles. So that's all my core for the core part of my demo. simulation run in real time with the four synchronized views. So the main map is for with the report path and obstacle, the SLAM map showing the map environment, the sensor view displaying the active perspective, and the path cost graph showing the real distance travel. The report successfully reaches the goal with while avoiding all the obstacles and updating its internal map. At the end, it displays the total path length, map coverage, and the confirming the effectiveness of the system. So for this assignment, I faced many challenges. The first was the most obstacle misalignment was solved by mesh grid and the round of functions. Then the sensor rays are not updating, so they have used so that user SLAM map properly were corrected by refining the raycasting. The RRT planner returning invalid paths was fixed by tightening the validation distance and the map accuracy. And for the inconsistent figure update, I used CLA function and draw now inside each loop. Lastly, the core modulatory was improved by moving the obstacle generation into a helper function. So yeah, this is all for my project. So this project successfully demonstrate a complete modular, robust indoor navigation system. It combines the RRT planning, SLAM mapping, and a sensor simulation into one functional simulation. This approach can be extended to a real-world application with the physical drone. And this is my references. So that's all for my video. Thank you very much.